Okay, this is the first of a couple videos I'd like to send to you guys. The first one that I'm going to do right now is a miniaturized redo of what we talked about in December, so that you have something to look at. Also, I might point out that I am not the best with this particular technology, so you'll have to put up with me a little bit, or I would like you to anyway. So let's see if we can get this going here. All right. So what we're going to be talking about is space filling curves. So that will mean a function. A space filling curve is a function. It's called a curve because its domain is the unit interval, and this will map into the unit square. We'll want it to be onto. That is the idea of space filling. So basically, we're going to take the unit interval. F will map every point of the unit interval somewhere into the unit square. And this mapping will be onto. We'll also want it to have this property, that if you take any interval AB from the unit interval, then F of AB, so I'm talking about the range. If you just look at what happens on F of AB, on AB of F, what happens? It will map into some region here, meaning that that range, the range just F of AB, will contain an entire disk, a circle filled in. So that is what we are going to mean by space filling. We can, of course, fill into more than just the plane. We can fill into three-dimensional space, but for us, this is where we're going to start. And we're going to use recursion to do this. And the recursive part will have just a few steps. The first step will be to take what we have, whether it's in the domain or the range, and partition it. The second step will be, again, to take this partition and linearize. Meaning you write it as a simple linear order, first, second, third, fourth, whatever. And it has to have the property that neighbors adjoin. By adjoin, I mean they intersect on their boundary. It's a partition, so they don't overlap. But ours will actually contain an edge. They will share an edge. And then importantly, we want to label these. And we want to label in such a way that we can use the labels to analyze what's going on. We'll get an arithmetic involved. There is a fourth step, and that fourth step is to return to number one. So since this is recursion, we're going to begin with a seed and do this process. And the process will leave us with regions in which we have to partition linearized label. And then we'll do it for each one of those and so on inductively for each natural number n. Okay, so let's begin in the range. So we'll begin doing this process by working in the range. Our beginning is the unit square. So we will begin doing this with the unit square. Here we go. So step one is to partition. Let's go back here. So step one is to partition. And we're just going to divide it simply into 4 congruent subsquares. So that's the end of step 1. Step 2 is to linearize. So this will be the first. So we have 2 candidates for the second, this one or this one. We'll take this one. Only one more candidate for the third, and one last candidate for the fourth. So here is the linearization. And notice that the 0th and the first intersect in an edge. First and the second intersect in an edge. Any adjoining pair from the partition intersect in an edge. And let's think of this as moving from an initial vertex here to a final vertex here, just for orientation's sake. We want to label these, and this is the ordering. This ordering also could be given with an arrow diagram, but we'll use these numbers. We'll label the actual square, J0, J1, J2, and J3. So these are the squares, J3 meaning this entire closed square here. And now again, J2 and J3 are neighbors according to the ordering and share an edge. And that's it. Oh yeah, there is a fourth step, and that says return to number 1. So now we have to partition again. Partition will be simple. We'll partition each of these into 4 congruent subsquares. Relatively congruent subsquares. And now at the second stage, we have to linearize these, and not just linearize each group of 4, but linearize the whole set of them. So what we end with, from starting with J0, we have to begin with J1. And so if this is again looked at as the initial edge of J0, the final edge of J0 has to adjoin J1. And so it's either this vertex here in the center or this vertex right here. We'll choose this one since our little picture goes through adjacent vertices. And then for J1, this will actually be the initial vertex of J1. The final vertex of J1 will adjoin J2, and so on. So this orientation helps us out when we need to actually define the ordering. So this will be 0, 1, 2, 3, ending up at the final vertex, 0, 1, 2, 3, ending up at the final vertex of J1, 0, 1, 2, 3, 0, 1, 2, 3. So there is the ordering. Now we actually have to label these. So we will take this first one, and it will be the 0th square of the 0th square. So this will be J00. This will be the first square of the 0th square, and so on. For J1, the 0th square of J1 is this one here, adjoining the 4th square of J0, and so on. So our labeling will be instructive for us, and it will be an ordered pair. That handles 4, and that handles 3, and then 4 is to return, so we do it again. This is the entire process for the range. Let's just do it in general. So if this is a J sigma, and let's say sigma consists of just a list of digits, a first, a second, and an nth for some n, and each of these a sub i's is 0, 1, 1, 2, or 3. Each of the a sub i's is this. There's a symbol for that. This means length n So it's a finite sequence of length n. And this means of 0, zeros, ones, twos, threes. So this is all of the length n sequences of zeros, ones, two, or threes. All right. So suppose we have a J sigma, and suppose that's an initial vertex of J sigma is indicated and a final vertex. I just picked random two adjacent vertices here. Then we need to partition. I'll try to use a different color. So we partition into 4 congruent subsquares. This will be the 0th. We order with 0, 1, 2, 3. And then the labels on these vertices, then the squares themselves will use these. So this one up here will be J sigma 2, for example. So using mathematical induction now, J sigma has now been defined for every n and for every finite sequence of zeros, 1, 2, 3s of length n. So that completes the entire induction partitioning recursive situation in the range. Let's take a look at the situation in the domain. So in the domain, we begin with the unit interval, and now we need a first partition of that unit interval. We're going to do the same thing. So we divide it into 4 pieces. I've chosen them to be equally spaced pieces. Label them left to right, 0, 1, 2, 3. Then we actually label those, not with J's this time, but with I's for interval. And then continue it. So now return, using recursion again, divide each one of those into 4. Let's pick one here. This interval, for example, is the 0, 1. It's the second interval of I2. So that interval is I2, 2. This interval is I3, 2. And in a similar way, then, that we did before, I sigma can be defined for every sigma finite sequence, length n, of the digits 0, 1, 2, 3. So this defines recursively, this defines I sigma for every one of those sigmas. All right. This is all that's necessary in order to define our space filling curve. And we can use the labels to tell what goes where. So let's take a look at that. So suppose we take an x from 0, 1. Then corresponding to the intervals that we chose, x has a base 4 decimal expansion. An infinite decimal expansion, and each of these d's is either 0, 1, 2, 3. Every element of 0, 1 has a base 4 expansion. This tells you exactly that x is equal to ID1. Let's make this more specific. 0, 1, 3, 2, 2, etc. So then x is in I0. X is also in I0, 1. X is also in I0, 1, 3. and so on. X is in fact the intersection of these. Their diameter goes to 0. Diameter of each one of these is 1 over 2 to the n. And this allows us to define f of x. So f of x will be this intersection, j0 intersected with j01 intersected with j013, etc. Each one of these diameters of these squares is 1 over 2 to the n times the square root of 2. So this intersection is nested. This intersection is just a single point. What's this thing right here? So this should be a J 013. And so knowing which x is here tells you what f of x is. So if we look at a linearized picture, x is 013, somewhere about here. Zero, 1, 3, 2, 2. So x is there. Where is f of x? Well, the first thing we can say is f of x is in J0, but then it's in J01. These were located 0, 1, 2, 3. So J01 is this square. Then it is in the third square of J01. And if we work that out, I think this is 0, 1, 2, 3. So it's in here, right here. And then it's in the third subsquare of that. So f of x is somewhere in that square. And if we look at the full intersection, that is f of x. This is our space filling function. And this is how we're going to analyze it. This arithmetic based on base 4 expansions of x is how we're going to analyze it. So that's enough for this first video. We'll talk a little bit about actual problems in the next one. Thanks a lot. And see you in the next video.